Good morning, everyone. I am Ranveer Chandra. I am the CTO for Agriculture and Food at Microsoft. My background is not in agriculture, but I spent several months growing up in my grandparents' farm in North Bihar in India. And I had started the FarmBeats project as a research project in 2015 to help address the world's food problem. As many of you know, we need to grow more food. We need to grow nutritious food to feed the planet without hurting the environment. Just to put these in numbers, we need to grow more than 50% more food than today's levels by 2050. And we need to grow so much food, even though the soils are not getting any richer, the water levels receding. And we need to get there without harming the planet. One of the most promising approaches to help address this problem is that of data-driven agriculture. What you could do, for example, with data-driven agriculture, one example is you could probably map every farm in the world and overlay it with data. For example, what is the soil moisture level 6 inches below the soil throughout the farm? What's the soil temperature level? What's the soil nutrient level? If you could build maps like this, it would enable technologies such as precision agriculture. As many of you might know, precision agriculture, which refers to the site-specific application of input, that is, with such maps, you could apply water where it is needed, pesticide where it is needed. And precision agriculture as a technique has been shown to improve yields. It has been shown to reduce costs because you use less water, less pesticide. It's also better for the environment for the same reasons. You're not wasting water. You're not putting more chemicals than are needed. In fact, it is just not the production side of agriculture, but the entire food value chain, all the way from input companies to tractors to farmers to production to the supply chain, the distributors, the food processors, even the consumer. Every entity in the food supply chain would benefit by using data and data-driven insights. But it is not just that. If you could start enabling sharing of data across the entire value chain, that is, from if the farmers could share data with others in the food value chain, if the distributors could share that data, it could improve new efficiencies. It could enable new business models that do not exist right now. And just to give a few examples, for example, you could track food as it goes all the way from farm. That is, if the farmers share data, if the food distributors share data, if the logistics companies share data, you can track and see how the food that you're eating came all the way from the farm to you. It could enable scenarios that are like track and trace. It could enable scenarios for food safety, where if there is an outbreak, you can know where this outbreak originated. Similarly, for precision agriculture, the digital advisory companies, they would love to know how what the farmer is doing in the farm, what inputs are they using. They could get information from the seed companies, from all the other entities to provide much better digital advisories. And now we are seeing a lot of talk around sustainability, where farmers could be paid money for using the right agricultural practices. If they could securely share the data in a privacy preserving way, you could then account for the amount of carbon that is stored in soil and reimburse the farmers, pay the farmers, incentivize the farmers for using the right agricultural practices. And these are just a few. There are many other such business scenarios that could be enabled if you could start enabling sharing of data across the food value chain. So as you can see, there are many, many benefits of data-driven agriculture. Yet, these technologies haven't really taken off. Just to put this in perspective, precision agriculture was proposed back in the 80s. We are talking of over 30 years since then, and the technology still hasn't taken off. And the key reason the technology hasn't taken off is most of these technologies are just not affordable. And I'll talk about a few of the challenges and how we have been working, how we have been doing research in some of these to help address those problems. The first reason existing solutions are expensive is because of the cost of connectivity in these farms. These farms are in the middle of, away from cities. They do not typically have good internet access. mostly non-existent. Sometimes, even though connectivity might exist when you plant the seeds, by the time the crops grow, the connectivity is gone. The question then is, if there is no connectivity in the middle of a farm, but the farmer's house might have some sort of connectivity, how do you transmit large amounts of data from the middle of the farm to the farmer's house, which is a few miles away? And this is not just sensor data. This could be drone data. This could be data from tractors or cameras and so on. To address this problem, we use a technology that I personally have been working on since 2005 called the TV white spaces. What the TV white spaces enables is, imagine if you have a Wi-Fi router that could go several miles. That would be cool, right? Right now, as soon as you exit your house, your Wi-Fi disappears. And the way we do that is by sending these signals, these Wi-Fi signals, over empty TV channels. So this is TV you watch using over-the-air antennas. You know, when you browse through TV on certain channels, you get a transmission. On the other channels, all you see is white noise. We built a technology where you could put these Wi-Fi signals in empty TV channels in a way that doesn't interfere with your TV reception in an adjacent channel. And we built this technology. We wrote a paper on this, which got the Best Paper Award in ACM SIGCOMM 2009. And since then, we've shown it to the FCC. This is made legal in the US. And the interesting thing about agriculture is that TV towers are where people are. You have TV towers in Seattle, in Boston. The farms are away from the cities. If you turn on a TV in the middle of a farm, most of these channels are white noise. And the more noisy channels there are, the more available capacity there is. And this is a technology that has been made legal. And we most recently, earlier this year, the FCC finalized rules where they allowed even more power, even more coverage in this TV spectrum. In addition to TV white spaces at Microsoft, we are exploring other ways to bring connectivity in the middle of the farm. For example, we are using private LTE in some cases. We are using space connectivity. We launched a new program called Azure for Space, where you could look at satellite connectivity in the middle of a farm. But this is one fundamental problem that is limiting the adoption of digital agriculture techniques. For many people in the computer vision audience, with computer vision community, well, if you're talking of computer vision, you need these images from the middle of the farm. And in order to get them, you need this connectivity. The second challenge we had to address is that of sparse sensor deployments. I talked about these maps. For example, the question supposes, what is the soil moisture level 6 inches below the soil throughout the farm? How would you build such a map? Some of you in the audience might know that soil moisture in a farm could vary from row to row. So really, to get an accurate map, you might actually need a sensor every 10 meters. But putting a sensor every 10 meters is expensive to deploy, to manage. It will come in the way of the farmer as the farmer does the day-to-day job. So the question we asked then was, can you build a map like the one you're seeing here using a sparse sensor deployment, using very few sensors? To address this problem, we decided to use aerial imagery to enhance the spatial coverage of sensors. The way the system works is you could either fly a drone with a camera at the bottom. These drones you can buy for about $1,000. They can cover large areas very quickly. And then once you get this drone imagery, you can then combine them and build these kind of panoramic views, these 3D point clouds, and then an orthomosaic of the entire farm. However, in some cases, drones are very expensive. Like if you go to sub-Saharan Africa or India, drones are not always feasible for smallholder farmers. An alternative approach that we have here is of tethered balloons. That is, you could have a balloon, a 4 to 5 feet balloon. What we built was a weatherproof mount where a farmer can put their smartphone with the camera facing down and a battery pack attached to it. And this is tethered to the ground, goes up 150 to 200 feet. And this thing can take images of the farm. In fact, in places where labor is inexpensive and the farms are small, someone could just walk around with the balloon. And then what we did was we used computer vision and AI algorithms to stabilize the imagery. And then we were able to stitch these orthomosaics using balloon imagery as well. In some cases where you don't have drones or balloons, we use satellite imagery. The way the system works then is once you have this image, we strategically place these sensors in different parts of the farm, a few of these sensors based on how many you want to put. Then wherever you put the sensors, corresponding to that, we have the imagery, the not just RGB, but multispectral or hyperspectral imagery. We take that to train the model, and then we use the trained model to predict these sensor values in other parts of the farm where you do not have sensors. This is a technology we evaluated for soil moisture, soil temperature, soil pH, and we wrote a paper on this, which was in NSDI 2017, where we showed that this technique of combining aerial imagery with these ground sensors can give you 3 times more accurate results than existing techniques that do not use aerial imagery, that just use the ground sensors. One of the things I talked about is satellite imagery. Well, satellite imagery is great to build these maps and for many other analysis, but one of the key problems with satellite imagery is that a lot of satellite images are just cloudy. That is, some studies have shown that more than 70% of the planet is covered with clouds. If it's cloudy, you really can't see what's underneath it. So what we did instead, we came up with a new technology called SpaceEye, which combines these optical imagery with clouds in some cases with radar imagery. This is another satellite that goes around the Earth that has radar in it. Radar signals penetrate through the clouds and reflect differently from different surfaces. We then use that to reconstruct using a new GAN technique or partial observation GAN to reconstruct what's happening below the clouds in satellite imagery. For example, in this figure, on the left is what you get right now. On the right is what we are able to predict on a day-by-day basis. As you can see, our results are very accurate, especially in 3 of the 4 seasons. We are getting over 95% accuracy in many of these experiments. Even though it's cloudy, we are able to say that the farm was tilled, the farm was irrigated, and all of that information. The third challenge is that of connectivity to the cloud. That is, I talked about how you could provide connectivity in the farm. You could transmit large amounts of data from the farmer's house from the farm to the farmer's house. But the connectivity from the farmer's house to the cloud is weak. Many farmers, they pay for broadband, but all they get is say 1 to 3 megabits per second connection. And just to put this in perspective, every time you fly a drone, you could be getting gigabytes of data. Sending this gigabytes of data over a 1 to 3 megabits per second connection is expensive. And it'll take forever to send all of this data to the cloud. So the key question then, and it's not just about weak connectivity. In some cases, this connectivity is intermittent. There is a farm in upstate New York where every time there was a snowstorm, there was a high likelihood that the internet connection goes off. So then the question is, if you could transmit large amounts of data from the farm to the farmer's house, but can't send it to the cloud, how would you bring benefits of all of this data to the farmer? To address this problem, our key insight was that many farmers have a PC in their house. If they don't have a PC, we would ship them a PC form factor device running Azure IoT Edge. It would sit in the farmer's house or office and do a lot of compute sitting in the farmer's house or office. A lot of computer vision would be done on this machine itself. Just to double click on this machine, on this Azure IoT Edge, everything you're seeing in this big gray box would run on the Azure IoT Edge. It would get data from sensors. It would get data from drones. It would generate the panorama, the orthomosaic. It would then combine it with sensors to generate the heat map. And this would then flow into the last column where we would work with partners who would build these services. People who know agriculture would build these technologies such as precision irrigation, precision pH, and so on. We also would have a scenario where you have cameras streaming data over the white spaces, and we run deep learning on the edge itself. And I'll talk about one of this scenario later. A lot of this data is then sent to the cloud lazily, where once it gets to the cloud, you merge with other data streams, for example, satellite data, weather data, and so on to provide additional services. You also have unique storage that sits on the farm. And we also have a web server for scenarios where if the system is offline, you would still be able to access the edge and perform some compute on this edge device. So this was all in research back until 2018. We did a lot of work. We did several deployments, and I'll talk about a few use cases. We deployed this in small farms and bigger farms. And like, for example, I'll talk about the first use case. This was of microclimate forecasting. So here, what we did was once you put a sensor in the farm, we would not only tell you what these sensor values are right now, but also what these sensor values would be up to 5 days in advance. And the way we did that was we combined sensor data with weather station data. So as you know, one of the important things for farmers is weather. They want to know when is it going to rain. They want to know what the wind is. Right now, when they look at the weather forecast, they get the weather forecast from the weather station, not what's happening in the farm. Instead, what we did was once you put a sensor in the farm, we take this weather station data and then train it to then start making very hyper-local predictions of what's happening in the farm. In this case, we trained the data over 50 weather stations across Washington state over the last 7 years at 15-minute intervals. We used that to train the model. And then when you put a sensor in the farm, we start making these hyper-local predictions. And as you can see in these graphs, if you look at just the red graph, this is one of the models that we currently use. The error is less than 8% in making these very hyperlocal predictions. On the bottom left, you find a testimonial from a farmer. This is a farmer in Washington. He farms 9,000 acres. When he takes his tractor out, he looks at these microclimate forecasts so to see what the wind is going to be in different parts of the farm. Because once you're spraying with a tractor, you want to make sure that the chemicals go where they're intended to go and not anywhere else. So at the bottom left, you can read the testimonial. He was looking to spray chemicals in his farm. This was a small part of the farm where there were a lot of weeds. And then he looked at the weather forecast, which said it was going to be 42 degrees. We said it was going to be 31. It actually ended up being 30 degrees below freezing. It was good he didn't spray chemicals in the farm because otherwise all his crops would have died. This is another use case we like talking about. This is a 4-kilometer stretch in upstate New York. The farmer in this case wanted to know how his cows are doing once they were out in pasture. So we flew the drone. We transmitted the data over the white spaces to an edge device sitting in the farmer's office. And within 30 minutes, we were able to flag things like from left to right, the grass is growing back well. There is a water puddle that needs to be fixed before the next planting season. The cows are pooping well, which is also important information for the farmer. This is deep learning on cow poop. This is where the cows are. This is a stray cow that needs to be herded in. All of this within 30 minutes of flying the drone. This is another farm. This is a small farm close to Microsoft campus where we used to do a lot of demos. We hosted Bill Gates here, several executives. Satya Nadella talked to this farmer multiple times. This is a small farmer who sells his produce in the restaurants in the Seattle area. And we show the farmer these beautiful pictures and overlay it with data. For example, this is a soil moisture map where we were able to flag that the bottom left part of the farm, bottom right part is still moist, even though there was no sensor over there. This is a pH map where we were able to flag that the dark parts of the farm are still acidic after the farmer had applied lime. And the farmer in this case should reapply lime before planting the seeds. This is a deep learning scenario where we were able to see how the cows are moving. We put these cameras in barns, transmitted this over the white spaces to an edge device, and see how the cows are moving, whether a cow is sick and needs attention, and so on. As you can see, this is like a baby monitor, but for cows. So we built all of these scenarios and then actually moved over to the product side, and we helped ship a product, Azure FarmBeats, which essentially what it is a cloud platform for agriculture. Right now, as you know, there are many ag tech solutions. What they do is these ag tech solutions would take a subset of any of these inputs to the cloud. And then what they would do in the cloud is they would then write their own proprietary schemes, their own data ingestion schemes, and so on. What we've done with Azure FarmBeats is, so in this case, for example, people could write their own applications, for example, for precision agriculture, precision nutrition, sustainability, and so on. With Azure FarmBeats, what we've done is we built a cloud platform where you could ingest data from different partners. Either it could be a sensor partner, a drone partner. We provide adapters where you could bring different types of data to the cloud. And once you get a lot of this data to the cloud, we then provide the geospatial processing, the cleansing, and preparing all of that data for AI so that we can then enable our partners to build their digital agriculture solutions on top of it. For example, just to give an idea of what this means is in Azure FarmBeats, you can specify a polygon, an area of interest. This polygon could be a farm, a field. And then for that polygon, we would bring in diverse data streams, satellite data, historical satellite data, weather data for that piece of land, and then allow you to merge all of this data and do large-scale AI on top of this data. We've announced this as a product in public preview in November 2019, and we've announced several partnerships with companies. For example, last year we announced a partnership with Land O'Lakes, where Land O'Lakes is building all of their digital agriculture solutions on top of Azure FarmBeats. Land O'Lakes is also working with us on sustainability. Similarly, USDA ARS, their agriculture research service, where with them we are working on, for example, for cover cropping. They're building their solutions on top of Azure FarmBeats. In addition to the product, we are also working on taking some of these technologies that we're building all the way to the consumers. One such thing we announced, we made a big announcement last year in January, where we announced that Microsoft was going to be carbon negative by 2030. What that means is that Microsoft will put back more carbon in soil than the amount of carbon that it generates. And we also said that by 2050, we are going to remove all our historical carbon emissions. That is all emissions since the time Microsoft was founded, which is a huge commitment. And we didn't stop there. We actually put together $1 billion as a climate innovation fund to fund this breakthrough research to make this happen. And how are we going to get to carbon negative by 2030? We actually did complete analysis. Part of it is going to come by reducing our own emissions. We are going to make our data centers greener. We are going to make our supply chain greener, both scope 1 and scope 2 emissions. But that's not going to be enough. We still need breakthrough techniques in order to put more carbon back into soil. As part of that, we had a unique RFP that we issued last year, where we had several organizations that applied for that were willing to offer their carbon credits for sale. One of the interesting things about agriculture, by the way, is that agriculture can help. These plants can help put more carbon back into soil. As you know, because of photosynthesis, these plants take carbon out of the air, and they can actually put this carbon back in soil. Of course, in order to do that, growers have to use the right agricultural practices. And this is one of the things we are investing in right now. And we are working with several companies on trying to figure out what is the best way to put carbon back into soil, and how can you, in an economical way, accurately estimate the amount of carbon that is sequestered in soil by using the right agriculture practices. In addition to that, we recently partnered with the Future Farmers of America, the FFA, where we've created a student kit. We've combined that with a curriculum, and we gave these kits out to these high schools. And essentially, the goal here is to equip the students, these students in high schools, to start getting used to data and AI and computer vision techniques right when they are in high school. This provides them the skills to apply for high-tech jobs. This also provides them the skills to start using data and AI and computer vision as part of their farming practices. One of the other recent work we did with universities, this was with Purdue University, where we created this dashboard for ag and food worker risk, where essentially what you could do, ag worker and food risk, where what you could do in this dashboard is, this was during the time of COVID. As many of you know, the farmers were affected. They couldn't sell their produce, and a lot of meat packing plants had to close, a lot of processing plants had to close. Through this dashboard, this was work done with Professor Jason Lusk, who's the head of agriculture economics at Purdue University. We gathered different data sources, brought all of those data sources to Azure, and then used Power BI on top of it to visualize this using a new metric that we came up with. And in this dashboard, you can click on any commodity. You can then click on any state and county, and you can see what's the likelihood of risk for that particular commodity in that county. In this case, one of the things we were able to flag was there was a meat packing plant in Yakima, which closed last summer, and we were able to flag that it would close over a week in advance. So there's a lot more to it, but because of lack of time, I'm going to make this presentation short. I wanted to conclude by saying that we are continuing to do a lot of work, and the way we work at Microsoft is through partners. Like, for example, even FarmBeats is not a farmer-facing product. The way it gets to the growers is through our partners, and we are very excited with a huge partner list, many companies that are betting on Microsoft to provide the technical infrastructure for them to help address the world's food problem. Thank you.